So before starting the second lecture, I would really say that I'm really happy to be here. It's my first time in Costa Rica, and I have had friends here since 27 years ago. There were two friends of mine were my schoolmate in Berkeley at that time. I had experienced the association with some professor from Costa Rica in different committee, and I have had several students coming to my school from Costa Rica. So it's my first time, but it's a real pleasure, and I hope to come back in the future. This second lecture will now move into the real subject of this short course, in the sense that moving from what has been introduced in a more critical way by Nigel Priestley, I'll try to give a few more details on the basics of the method and on how to deal with the seismic action, which is, of course, one of the several critical issues that have to be dealt with. Nigel was finishing his presentation talking about limit states or performance level. And actually, if one thinks in terms of performance level, one could immediately understand that there is even there a good reason to design starting from displacement rather than starting from forces. Actually, if you look at this sketch, which is not in your slides there because I just added it 5 minutes ago, it is clear that if you accept to define performances as they are sketches here, you will immediately understand that force is not a good measure for performances. And after all, when we are dealing with structures of all sorts, when we are dealing with buildings, with bridges and so on, we are more interested on global performances than on what happens locally. And actually we are really interested in what happens locally, only because there is some correlation between what happens at the base of a column or in a critical part of a beam and so on, only because there is a correlation between this and the general performance. But the question that people and authorities and decision makers are asking are not what will be the strain in a steel bars or something of this sort, but the questions are rather, will the structure be usable? Will a building be inhabitable? Will a bridge be usable by unrestricted traffic? These are the kind of questions that we should answer as engineers. So the point then is that direct displacement-based design is not usable and is not to be preferred simply because there is more correlation between displacement and performance, but also for another series of reasons. And it is important to immediately note that from a structural point of view, damage is strain dependent. We do this all the time. When we look at the performance of a section, and I will enter in more detail into this aspect, we are looking at the elongation of the steel, we are looking at the shortening of concrete, and we are somehow relating local damage to strain. And then when we are somehow integrating the local damage into more global element level, structural level, we still have a strong correlations between damage and strain. There is more than that, because when we are looking at the structure as a whole, in many cases, we could be even more interested in non-structural damage than in structural damage. And essentially, non-structural damage is related to strain, in the sense that it is related to the interstory drift or to the global drift of a structure. You know the drift means a displacement divided by a height, so essentially a drift is a rotation. So structural and non-structural damage are essentially related to rotation or to curvature, and integrating curvature you get rotation and so on. What is done when someone is designing using force-based approaches is just to check at the end, and this is not always done, that displacements are compatible with the performance of the structure. But to be compatible does not mean to be close to. It does only mean that there is a check that the expected displacement is not larger than the demand which is correlated to that performance level, to that limit state. In a way, we could design structures that are far away from being challenged by the displacement demand, or design structures that are close, but there is essentially no correlation between the design phase and the performance which is obtained. On the opposite, what we will try to describe in these 2 days is a design method that tries to achieve a certain displacement level. So it's not just a matter of designing safe structures, but it's a matter of designing structures where there is not any exaggeration of the protection, which means to spend money, to spend too much money, and in a way not to have money for other things. So let's have a more detailed look on what is done with force-based and what is done with displacement-based. The essence, which has already been introduced by Nigel, is that when we are dealing with a force-based approach, we are assuming that we know the stiffness of the structure. Normally, you enter an acceleration spectrum with a certain period of vibration. And therefore, since there is a direct correlation between period of vibration and stiffness, you are assuming that you know the stiffness at the beginning of the design. Normally, it is not even checked after the design has been completed that our initial assumption on the stiffness were correct or not. And in many codes of practice, there are simplified formulas to guess what the period of vibration of the structure will be, and these formulas are not very reliable, as Nigel has already discussed earlier. The second point is that after having entered the acceleration spectrum and having then read an acceleration and multiplied this acceleration by a mass and possibly having reduced it by a force reduction factor, there is the second problem: how to distribute this total base shear between the elements that can contribute to that. And what we normally do in a force-based approach is to distribute this base shear in proportion to the stiffness of the elements. This is just an heritage of what was done centuries ago, when the stiffness was directly related to the strength. In a way, we are still using the Hooke law. You may remember that Robert Hooke expressed the Hooke law in 1776, 72, something like that, in the second half of the 17th century. And we are still there on the proportion between stiffness and, well, let's say the proportion between elongation and strength on the base of stiffness. But we are doing exactly the opposite today when we are designing, even with a force-based method, because what we are doing is that we are assuming that the structure will yield. The structure will reach its strength. And if we assume that, the logic is completely different. Actually, if you think in these terms, you could say that the acceleration that the mass of the structure will experience has nothing to do with the action. The acceleration that the structure will experience is simply the strength divided by the mass, nothing else. In direct displacement-based design, there are two completely different assumptions then. The first one is that at the beginning of the design, we do not know the stiffness of the structure of the period of the structure, but we know at what displacement level we want the structure go during the action, during the seismic event. And of course, this displacement could be different depending on the performance level, and therefore it could be different depending on the seismic action level. So we could say, for this specific level of seismic action, we want to design for this displacement. This, in essence, is the first point, which is intellectually different, logically different from a force-based approach. We want to start from a displacement, and we want to enter a displacement spectrum with the displacement to read what period of vibration the structure must have to go to that level of displacement. And therefore, if we then get the period of vibration, we calculate the stiffness, and if we multiply the stiffness by the displacement, we get the strength, the base shear that the structure should sustain. The second point is that the strength, the base shear, is not distributed to members in proportion to the elastic stiffness. We will discuss later today in which proportion this should be distributed, because if I now say that it should be distributed in proportion to the strength of the element, you will immediately say we do not know yet the strength of the elements. But certainly we will not distribute it in proportion to the stiffness. So the fundamentals of force-based design are rather simple in a way. This figure has already been shown, but it's, I think it's convenient to go several times on the same concept. If you are dealing with a simple structure, such as the one which is depicted there, so for example, a bridge bend, you could assume that you have a single degree of freedom model which is similar to that structure, that you could use for the design of the structure. And you could assume that you know at what level of displacement you want to design the structure for. When I'm saying the level of displacement you want to design the structure for, of course, in this figure, I mean the displacement which is indicated with delta D. But the other point that we should make very clear is that you could guess very reliably on the base of the geometry only what the delta Y, the elastic limit displacement, will be. And I will show this in a minute. But if you know at the beginning of the design what the delta Y will be and what the delta U will be, then you will also know at the beginning of the design for what level of ductility you want to design. And if you have a guess about the level of ductility you want to design, and you accept that there is some correlation, and this will again be discussed in some more detail soon, in a few minutes, there is some relation between displacement ductility and equivalent damping, then of course you could guess what equivalent damping you are going to have, and you could use this equivalent damping to correct the displacement spectrum to go from a standard displacement spectrum with say a conventional level of damping to the actual displacement spectrum, the one that you will be designing for. You should note, however, that if you should make a mistake in the evaluation of the ductility, certainly you will move on this horizontal axis, but moving on this axis, you will certainly change the level of damping, and you will certainly change the spectral shape of your demand, but the modification will be in the range of percents, not in the range of times. What I mean is that you will be correcting, or you will make a mistake, that could be that you will end up there having something which is 0.18 instead of 0.19 meters, which is very different from what happens in the case of a force-based approach when you assume a completely wrong force reduction factor that could vary between, say, 2 and 8 or something like that. So the sensitivity to mistake of the procedure is much less. And this is just the same, but and you have already seen this too. I mean, this is just, the errors are just indicating that you enter with an estimation of the displacement ductility and you read the damping, and then you enter with the displacement demand and you read the period. And when you have the period I was saying, you can immediately calculate the stiffness. The formula is there, but it is trivial for anyone who is dealing with engineering. Now, if you go to your structure, you enter with your design displacement, and now you know the strength of the structure because you know what there is indicated with KE, which is the stiffness that was coming out from the previous step. So multiplying displacement by stiffness, you obtain the total strength that you have to assign to the structure, which is the answer to the first of the questions that we were posing. And this again is the example that Nigel has already worked out, but, so I won't go through it again, but clearly it's very easy and trivial to do something of this sort. Now, I don't want to spend too much time on this slide, but this slide is just trying to give an indication on what are the fundamental steps that you will go through if you are designing using a force-based approach, and what are the steps that you will go through if you are designing with a displacement-based approach. Unfortunately, what happens with forces is that there it is written displacement, okay, revised stiffness, and this sometimes happens, but normally there is not a check to verify whether the stiffness that was assumed at the beginning of the design is the correct stiffness or not. Now, let's see with single degree of freedom structure, and let's go into some more detail into the procedure. I was saying that the structural displacement limit is strain related, that non-structural displacement limit is drift related. So already at the beginning, you have two limits that you should consider for which one of the limit states that you want to consider. And in some cases, one of the two will be governing, in the other case, the other will be. And you may be surprised on how many times the drift that you have to use not to have too much damage on a structural element will be governing the design. This will be particularly the case in most high-rise buildings. If you go beyond a certain number of stories, this is likely to be your limit, the limit that you should consider. Nigel was showing this as one of the first slides of his presentation, when he was showing that if you look at what is the limits at which you need to have you can have some ductility or you cannot have some ductility, there are many more cases where you cannot really exploit ductility because otherwise the structure will be too flexible, will go to have too large displacements. And this is again something that is not recognized when you are designing with force-based approaches. If we look at a simple example like that of a bridge columns like this, it's very easy to recognize that if you look at the strain at the base of the columns, at the critical region of this column, you are going to have a certain elongation on one side and a certain shortening on the other side. Now, if you should ask yourself what will be the yield displacement of this structure, well, you will immediately answer that the yield displacement of the structure will correspond to a situation where either one of the two sides of the base of the columns will attain the yield strain. But you can also immediately recognize that up to that stage, the two strains on the two sides of your column will be reasonably similar. What I mean is that the neutral axis will be not too far away from the middle of the column, which means that if you want to guess what the displacement at yield will be, you could assume at the first stage, without any calculation, that this will correspond to a situation where you are going to have approximately the yield strain on one side and the yield strain to the other side. So this means that the curvature, the yield curvature at the base of this column will essentially be 2 times the yield elongation divided by the depth of the column. So you can immediately guess what the curvature, the yield curvature will be. I'm repeating some stuff that Nigel has already presented, but I think it's worthwhile to repeat things to have a clear idea of what happens. And if you now know the yield curvature, and you know that you have a structure which is free on the other side, you are going to have a triangular distribution of curvature, and it's very straightforward to integrate that curvature to get rotation and to integrate multiplying by a distance to get a displacement. So what I mean is try to explain what is written there, where it is written that the total displacement of that column at the top of the column will be the sum of the yield displacement plus the plastic displacement, and the yield displacement could be assumed as the yield curvature multiplied by the height to the square and divided by 3. And that is simply the integral that I was describing. So this means that the first part of that sum it requires only 1 minute of calculation, not more. The second part of that sum is different, because there is the part that will depend on what level of displacement you want to attain at your performance level. And what is written there is simply the usual equation that you know very well, which is the equation that considers to have a plastic hinge length multiplied by a height and multiplied by the plastic curvature. So in a way, what I'm trying to say is that with a structure like this, you can really guess at the beginning the 2 displacement levels that we were willing to have to start the design process. And in his talk, Nigel was showing that this is not true only for a simple structure like this, but also for much more complex structures that will be discussed again tomorrow morning. In a way, I'm going again to this slide because I think that now we have had more time to think about it. What I'm trying to say is that the realistic assumption is what we have on the right and not what we have on the left, and which means that we can assume that what the yield curvature will be and not what the stiffness will be. Now, at this point, the next key issue is just to define what the displacement will be, the total displacement, the design displacement. And as I was saying, this displacement will be the lesser between the displacement that is related to structural damage and to non-structural damage at that level of performance. But I want to underline the fact that this procedure is very flexible. It's very flexible means that you could use any displacement of your choice to go ahead with the procedure. And it would even be possible, and this may happen in the future, to add a third, say, verification, which is the verification on what the residual displacement will be. The only difficulty in doing that is to have a correlation between residual displacement and design displacement, which is normally not that difficult. And as you know, residual displacement is actually what you have at the end of an earthquake. When you go and see what happens after an earthquake, this is what you see. And this is essentially what you look at to decide what to do to a structure. So in the future, this could be an interesting parameter to look at. Now, ductility, I was saying, is also known at the beginning of the process. And on the base of ductility, we should try to arrive to calculate what the damping value will be. But before doing that, these equations that you see here are essentially the equations that allow you to have a better evaluation of what the displacement, the yield displacement will be. Those figures that you see there, 2.25, 2.10, 2.0, 1.70, may be a bit strange, because when I was saying that an estimation of the yield curvature could be 2 times the yield elongation divided by the depth, you may have thought this must be an upper limit, because I said that you are going to attain the yield elongation on one side, and on the other side you have not yet attained that level. But you should not forget that these equations are design equations, and therefore they should take into account also some level of yield penetration. If you look at the force displacement curve of a structure, normally you are approximating this force displacement curve with a bilinear approximation, and your yield point does not correspond to the initial yield of the first bar in a section, but is certainly more to the right of your diagram, because you are trying to integrate the global response in terms of force displacement. So those values have been somehow checked against a large number of numerical and experimental tests, and their capacity of approximating the displacement, the yield curvature, and therefore the yield displacement of structure is very good, and actually is essentially within 10% or so. And the other 2 equations are equations where instead of a curvature, a rotation is represented, and it's just a repetition of the equations that Nigel has been showing earlier. And then if the structure is a real single degree of freedom, which is free at the top, then you can immediately find out what the displacement, the yield displacement will be if the structure is still a simple degree of freedom structure, but has different kind of constraint or restraint, then the integration, of course, gives different values. Now, the second issue is the evaluation of the equivalent viscous damping. And the equivalent viscous damping is crucial in the whole process, and actually is essentially the kind of free parameter that could be correlated somehow to the force reduction factor in a force-based approach. With the difference that we have some way of predicting its value with a much more physical and with a much more trustable process. So clearly this equivalent damping will be the combination of an elastic damping and of a plastic or hysteretic damping. Of course, this is true if the dissipation will be through hysteresis, which is the case of standard steel or concrete structure. It could be, instead of hysteresis, could be something related to some Coulomb friction or to something else if the structure is governed by some other kind of behavior. Tomorrow, for example, we'll be discussing hydraulic dampers, and in that case, of course, it's not hysteretic, that part of the dissipation. So the point is that some of us have been trained in the past with some sort of equal displacement rules that assume that if you have a fatter or thinner hysteretic cycle, you will have anyway the same displacement demand. This does not make any physical sense. You could say that they are approximately the same, but certainly if you imagine the response of a pre-stressed structure which has essentially a nonlinear response, but this nonlinear response is essentially not a non-dissipating response. It goes back and forth on the same line. Or you have a fat loop. It is intuitive to accept that in the second case you are going to attain a lower displacement because you have a large damping. You are dissipating energy. And this, of course, is also clear if you look at the standard equation that governs the response of a structure. Now, a few more words on the influence of elastic damping. This is something that Nigel has been discussing. It is clear that if you look at elastic damping, you have some reason to consider elastic damping. Why to put those 5% or 2% or whatever you want to put. And these reasons are essentially partially because of some kind of real viscous damping, but partially because of other kind of dissipation in the elastic range. For example, the dissipation due to interaction with soil, or the dissipation due to non-structural elements. But if you look into each one of these elements, you will immediately realize that after yielding, none of them is still an important factor. And in fact, for example, if you think in terms of foundation damping, when after the structure has reached its strength in the soil, essentially nothing more happens. So there is no more dissipation there, and so on and so on. So the conclusion is that after you have gone into the plastic range, in principle, you should use a tangent stiffness model, because otherwise you will be inappropriately increasing the contribution of the elastic damping. Now, I was saying that you can have different kind of shapes. These are examples of different shapes. I want to skip that. But I want to show you something to prove experimentally what I'm trying to discuss. So now imagine to take a very simple structure, a kind of a real bridge column in the laboratory, to design it carefully, and after you have designed it carefully, to put it in the lab and to test it statically with an appropriate vertical load and with some horizontal cyclic loading. And you end up having some very nice cycles, and you can simulate this response, this nonlinear response, with fiber elements, like this program Seismostruct is a fiber element program, or you can try to have a model of the response with other programs. This is a simulation made with Ruamoko, which is a concentrate plasticity model. Now, if you have done all this, you may trust that you know your structure in detail. So you have gone through a static test, you have gone through cycles, you have done everything. Now you take a record, any record you wish, and you go and use this record to predict the nonlinear response of this structure. And you use the value that you know. So you are using the actual values, those coming from the cycles in the laboratory. So if you do that, and then you take the structure and you put it on a shake table, what will happen is that you are expecting to have exactly the same results as in the case of the static tests, or as in the case of your model. The only difference is in the simulation of damping. And you put it there and you go for your test, and of course you try to go for some significant level of ductility, actually to go to something which is similar to what you have done in your static test, and what you may obtain if you are accepting to spend a lot of money in instruments like those that are down there. You may obtain something like this. And what happens is that if you look at the simulation of this structure, you can see here what you get from a simulation using the initial stiffness damping, or if you use a tangent stiffness damping. And you can see that the displacement demand predicted is very different. You look at those big cycles there, you can see that it can be as large as 1.5 times. And if you have a demand of 1.5 times when you are closer to a situation where second-order effect can govern the response and so on, you may have the difference between a structure that stays there and the structure that does not stand at level of displacement. And these are the figures, actually. You see the experiments and the prediction that you have with zero damping, with a fiber element, or with a Takeda tangent stiffness in case of a concentrated plasticity. And you see that those predictions are not too far away from the experimental demand, but if you use a Takeda initial stiffness, you have some prediction which is in the range of 50% less displacement demand. Now, this is just to conclude that we must use tangent stiffness for what concerns the elastic damping. But for what concerns the hysteretic damping, we should go back to our basic concept and see that we have a certain kind of energy dissipation due to the hysteretic cycle of the structure. Now, the point here is, can we find some equivalence between the energy dissipated in a cycle like this and the energy dissipated by some sort of viscous damping? Well, if you look at the problem, this is what you normally do with viscous damping. When you use viscous damping, a larger viscous damping means that instead of having a structure that is responding linearly, you have a structure which is responding along a kind of an ellipse. So I'm not saying that I'm so lucky in the sense that I could put something like that they are so similar that I could say, okay, this is fine. Because of course, if instead of having something like this, which is something which is called thin Takeda or something like that, you may have some different shape. Of course, the shape of your red oval will be quite different. But in a way, the point is, we want to have something where we have approximately the same energy dissipation in both cases. And to have the same energy dissipation means to have something where you are predicting the same level of displacement reduction due to the two effects. We should understand this and recognize that this is not perfect, in the sense that you know that viscous damping is a multiplier of velocity. And in a test, when you are going through something like this, velocity is certainly not constant. You also know that if you do something of this sort, you write down an equivalence where you take an area which is an energy, and you divide it by another area to have a coefficient. You are doing this for a certain level of displacement. So in a way, you are somehow assuming, if you do that without any other consideration, that all the cycles in your response will go to that level of displacement. And this is not the case, of course, because in an earthquake, you are going to have maybe 2 or 3 cycles at large displacement and many other at smaller displacements. So you have lots of approximations, and the only way to see whether these approximations are acceptable or not is to go through experimental testing and numerical analysis, and to see whether that sort of equation is acceptable as it is, or you need some correction to make it closer to reality. But on the other side, we should also consider what I already pointed out earlier, which is that if we make a mistake, this mistake will be a mistake on a small factor. And therefore, it will not necessarily be very important on our prediction. So what has been done by a large number of PhD students over years is to go through simulations using real accelerograms, through simulation using spectrum-compatible accelerograms. And as you can imagine, this is very different, because normally spectrum-compatible accelerograms have a larger number of equivalent cycles, of large cycles with respect to real accelerogram. So you can have input that are very different, but what you obtain is that the results are quite similar. The other difference is that you can use very different hysteresis rules, and here you can see some of them that are defined as elastic-plastic, bilinear, and so on, and of course also some sort of flag shape that you could obtain combining possibly pre-stressing and energy dissipation and so on. Tomorrow we will see something of that sort, which is something that we may like very much because we are reducing the residual displacement. Of course, also reducing the energy dissipation, but maybe not at a very large, well, maybe it will be half of the elastic-plastic there. Well, what you obtain is some sort of curve of the sort that you can see here that will give you some relation between displacement ductility and equivalent viscous damping. And this curve will depend, of course, on the fact that you are using a cycle like fat takeda or flag or thin takeda or elastic-plastic. And you can see that if you increase the displacement ductility to a certain level, there is a tendency for these curves to become flatter. And therefore, this implies that when you are going to larger displacement ductility, you are making smaller mistakes in the evaluation of the equivalent viscous damping if you are making some mistake on ductility because the curve are getting flatter. The other thing that we should consider is that we are not using either an initial stiffness nor a tangent stiffness, but we're using an equivalent stiffness. And if you look at the kind of viscous damping in terms of force and displacement, you have an oval if you are going for a constant stiffness, but this oval is modified very significantly in the case of a bilinear response, for example. It is modified, as you can see there, in the sense that when you are in the more vertical part of the cycle, you are on the oval, and when you are on the second line where you have a lower stiffness, you are in a smaller oval, which is related to a smaller level of stiffness. So there are also some corrections that should be made under this respect, because in a way you remember that what you are looking for is to have a good evaluation of the damping to be associated to that level of stiffness. So it is not a simple procedure if you want to go through all the steps, because you have to consider different corrections if you are assuming a tangent stiffness or an initial stiffness. And of course, the correction that you have to consider have a different sign, because you are using something, you're using a stiffness which is intermediate between the initial stiffness and the tangent stiffness. But what you end up with can be relatively simple formulas, like those that you can see here, that are in the book, that have a similar structure, where you can see that there is always some real viscous damping, and you see there 0.05, and it could be a different figure, of course. And you have the other part where they have a similar structure, which is ductility minus 1 divided by ductility multiplied by pi, and there is only the multiplication factor that changes, and of course this multiplication factor is larger when you have larger loops and smaller when you have smaller loops. But if you look at, for example, if you look at concrete frame building, thin takeda, if you look at steel frame building, Ramberos's good formula, and you look there, you have a 0.565 or 0.577. What I'm trying to say is that for a similar level of ductility, you are going to end up with a similar level of equivalent damping. There are other factors that you should consider to correct this value. I cannot enter in a great detail into this. Of course, you will find all this in the book, but the point is that what you obtained in terms of relations between in elastic time history analysis and area-based elastic viscous damping can change as a function of the ductility level that you reach. So in a way, let me go here first, you will need to use a different approximate curve depending on the level of area-based viscous, on the ductility level that you are attaining. And you can see this in this case as an example. Here you have a flag type hysteresis loop, and you can see that the red oval that you obtain is of that sort. That actually is a representation of the formulas that you see there, where you have the calculation of the equivalent viscous damping as a ratio between the hysteretic area divided by the equivalent area in the case of the oval, and you end up with something that, of course, changes significantly if you are assuming a different level of ductility. Because if you are assuming a different level of ductility, you are changing the value in the formula there. But having different level of ductility, you should also come here, and this yellow line are exactly those coming from that figure there. So in a way, what I'm trying to say is that if you are designing, for example, a ductility 2 for a certain level of damage and a ductility 4 or 6 for another level of damage, you will end up with different correction factors to be used. Now, I will enter into the second part of this session, which will be dealing with the characterization of seismic action. And as you will see, there is a very strict correlation between what I've been discussing up to now and the definition of seismic action, because after all this discussion of equivalent damping and so on have the purpose of correcting the displacement spectrum and nothing else. So in a way, we have to see how to define the earthquake demand in terms of displacement spectrum and how to use the factors to correct this displacement spectrum. So we will have to look into some more complex kind of demand like time histories to see what response spectrum will come out, and in particularly I will try to discuss what kind of displacement spectrum you will obtain deriving the displacement spectra from acceleration spectra, or what you will obtain if you use more rational approaches to derive directly a displacement spectrum and a displacement demand from some more basic characteristics of the earthquake. And this will be essentially the influence of magnitude and distance. And of course, we will see what damping reduction factor could be appropriately used. And you will see that most of the complication that I was trying to explain probably I was not very good in that, but was trying to explain, will become simpler when you go to practice. So, just to start, let's have a look at three accelerogram, three real accelerogram. This is one of the several accelerogram recorded at the Whittier-Narrows earthquake in 1987. The magnitude was 6.0, and there was a peak ground acceleration around 0.4 g. If you now look at one of the accelerograms recorded at Northridge, 1994, a magnitude of 6.7, you see that the peak ground acceleration here is in the range of 0.85 g. And the third one of the Kobe records, 1995, you may remember that, strangely enough, Kobe and these last two earthquakes were the same day. They were both January 17th. I don't know if this has something to do with them, but it is true. And you see that in this case, the peak ground acceleration is very similar, is 0.8 g. Now, if you look at the ground displacement, Please note, ground displacement. This is not the peak displacement demand in a spectrum. It's the ground displacement. But if you look at the three levels of ground displacement, in the case of Whittier, you had 1 centimeter. In the case of Northridge, you had 30. In the case of Kobe, you had 20. Just roughly speaking, what I'm trying to say is that you had a ratio of not more than 2 in the case of acceleration, and you had a ratio of about 30 in the case of displacement in these two cases. This should at least put a warning in our brain. Maybe there is something that make us thinking that the correlation between peak ground acceleration and peak ground displacement maybe is not as good as we might thought. Those of us that have been studying in the 80s may remember the studies by Newmark and Dole and the booklet by the ERI, where there were given relations between peak ground displacement, peak ground acceleration, and so on. How do you use this with these earthquakes? I'm not saying that Newmark and Dole were saying wrong things, but they had data that were the data of the 70s. There was no digital record. There was just, everything dealing with displacement was based on integration, with baseline corrections, with filtering, and so on. They were relatively poor data. You may remember, I will say again something on this, and forgive me from time to time saying something in parentheses, but you may remember that the first spectrum was derived by Maurice Biot in 1933 or something like that, which was the time of the Long Beach earthquake. And most people believes that the first spectra were coming after the 1941 El Centro earthquake, because the El Centro earthquake has been the earthquake. We have been all using El Centro for something. But it was not true. It was the first analogic recording of earthquakes were in the 30s. And there were very clever people at that time. Anyway, what can you say about time history observation? Well, certainly, we very, very well know that acceleration time histories give an incomplete picture of an earthquake. And particularly that frequency content may be influenced by distance to the source. If you want to talk about the distance from the epicenter, or if you want to talk about the distance from the fault, or if you want to take some equivalent distance, it's, many seismologists are working on that. I don't care too much. But the distance to the fault is a crucial point. And the third point is that displacement time histories expose large differences between earthquakes with comparative similar peak ground acceleration. So now we'll have to make some extensive use of response spectra. And I will certainly not try to discuss here. We are not in a basic course on dynamics of structures. I will not go back to discuss what a response spectra is, but certainly I want to underline that essentially a response spectra is just a tool. It's just a tool to have something simple to design, nothing more than that. And of course it is generated for specific level of viscous damping. And of course it is possible, well, in general they show an elastic response. To derive non-elastic spectra is always implies some other level of correction and so on. Let's forget about that. Now let's have a look at what happens if we look. Anyway, this was the kind of things that Maurice Biot was doing in 1933-36. But anyway, it doesn't matter. Let's look at the spectral shapes for Whittier and have a comparison of the acceleration spectrum and the displacement spectrum. As you can see, the acceleration spectrum is a rather narrow spectrum with a peak that goes up to about 0.8 G acceleration for a 5% damping. And of course, if you increase damping, you will see that the peak is coming down, as you will expect. But in the descending branch, you don't see much difference when you are changing the equivalent damping. And something similar happens if you're looking at the spectral displacement. You can see that, well, we all know that spectral displacement in the past has always been assumed essentially as a linear spectrum, always increasing. What we see there is a rather different picture, in the sense that we see something that goes up linearly only in a first branch for maybe up to 0.3 or 0.4 seconds, and then it has an irregular shape, but essentially it goes to a kind of a flat plateau in the range of, say, 1 centimeter. I am sure that all of you well remember that the peak ground acceleration is essentially the peak ground displacement is essentially the displacement that you see in a spectrum for a very large period of vibration. So in this case, you see that the flat part, which is beyond, say, 2 seconds, is essentially the peak ground acceleration. So what you see there is that we have gone up to some amplification, and then we have come down to the peak ground displacement. Now, if we look at the north ridge, we see something similar but different. And what is really different is that instead of having something which has just a peak here and then it goes down rapidly, we have some fat area here. And this area is more responsible of producing large displacement than the level of the peak here. And as you can see two things here. One is that you go up, and this could be considered somehow linear. Then you go down, and you may remember that the peak ground displacement at Northridge was about 30 centimeters. So here, we have not yet gone down to the peak ground displacement. We are still in an amplified area. The other thing that you should note is that here the equivalent viscous damping has a significant effect in reducing this peak. If you look at the level of this demand, which is with a 5% damping, you are in the range of 80 centimeters. If you look at 20% damping, you are in the range of, say, 40 or 45. There are two things to be noted here. One is that the peak spectral displacement is more than 2 times, maybe close to 3 times the peak ground displacement. This makes sense. This is something that also in the 80s we knew. And the other thing is that even in this case, where the damping has a large effect, the correction is in the range of less than 2 when you go to 5% to 20% damping. And this is just to conclude our comparison and look at the case of Kobe, and you see something again where you have some significant effect, and you remember that in Kobe we had a peak ground displacement of about 20 centimeters. So you may see that here we are not too far away from reaching the level of the peak ground displacement. Now, the point now is we have to discuss looking at these examples and see again that from acceleration we don't get a clear picture, but the point is how should we derive a displacement spectrum, which is what we need for our approach. What we would do immediately without any problem is to go back to the basics of dynamics that we know quite well, and to know that simply multiplying by something which is related to the period to the square, we can pass from one spectrum to the other. If you go back and have a look at your books on dynamics of structure and you look at this, you will see that this correction is a correction that comes from the Duhamel integral, and you will see that this is just an approximation. This approximation works well only in a certain range. But anyway, this is not the point. The point is that if you have a structure where you use an equivalent stiffness, you have a structure that normally has a much longer period of vibration than what you normally do when you design with force-based, and often you use the initial stiffness, the gross stiffness of the structure. So your period of vibration that you want to look at is normally much longer than what you are used to. Partially because of the second stiffness, partially because, as Nigel has been pointing out earlier, we are always underestimating the period of a structure, even if we stay with the initial stiffness. Now, if you look at that and you see what happens, is that in many cases, if you look at the acceleration spectrum, to go from, say, 3 to 4 seconds period, the acceleration does not change too much, first. You might also be in an area where, in many codes, you have to use a minimum level of acceleration, and therefore there is no difference, essentially. But when you go to a displacement spectrum, you may well be in the area where you're still increasing, or you may not. But you can have very significant differences because the displacement demand can increase linearly. Or you could have no difference if you are in the plateau where you have essentially the same displacement demand. So what I'm saying is that a change in the stiffness and therefore a change in the period of vibration is more relevant when you are dealing with a displacement than when you're dealing with acceleration. But please, don't think that I'm saying that you are making a smaller displacement here. I'm simply saying that you are making displacement that you don't care, and you will end up with very different displacements there. So you are, again, instead of saying having a better situation because the spectral acceleration is less sensitive, you will end up with something that you do not know. So you are adding mistake to mistake. Anyway, if you go back and we discuss what should be the shape of a displacement spectrum, what is today accepted by seismologists is to have, in principle, something like this. And you may recognize in this shape something which could allow to fit the spectral shapes of Kobe and the spectral shape of Northridge that I was showing, saying that you are going up to a certain level of amplification, you are somehow staying at a certain level of amplification, and then you are decreasing to the peak ground displacement. The problem is that normally the value of the period that is indicated there as TC, and C is convenient because we call it also corner period, so C is also the initial of the word that we use to define it. This level here can already be, and I will show something on this, in the range of, say, 2 to 5 seconds, something like that, depending on the kind of earthquake. And this point here, the area where you start coming down, may well exceed a level of 10 seconds or 15 seconds or so. May well, not necessarily is. But what I'm trying to say is that for designing, we are only interested in this branch and this branch. We are not so much interested in what happened here unless we are dealing with a structure that will be behaving in this range elastically. If you have an elastic structure that has a main period of vibration of 15 seconds, maybe you go there. But then you will immediately recognize that there are also other modes of vibration that will be in shorter period. The other point that you should not forget is that if you consider that a structure is increasing its period of vibration due to damage, and you say, I could go in this area here because of the damage of the structure, you should also recognize that to go down here, you have to pass through this plateau during the damaging of the structure. And this is another reason why you don't care too much to what happened there. So in a way, what I'm trying to say is that the spectral shape that we want to use somehow is a bilinear shape, which is what we were starting using since the beginning this morning without giving a clear explanation on why we were using a displacement spectrum shape with a bilinear approximation. And this is actually what happens if you try to derive displacement spectra from acceleration spectra. You have, as you know very well, you have a first branch where the acceleration spectrum is increasing linearly, and therefore the displacement spectrum is increasing with t to the cube. But this is for a very short period range. Then here you have something constant, and there it goes with t to the square. Then you have the long descending branch that normally in code spectra decrease with 1 over t, and therefore there is increasing linearly with t. I'm simply multiplying by t to the square, as you have understood. And then, and this is, has been done in relatively recent time in acceleration spectra, there is a point where they say, where the code makers say, then go down with 1 over t to the square, and this is has not been done for the acceleration spectra, has been done for the displacement spectra, to have a cut at the level of the displacement demand. If, on the opposite, you take a minimum level of acceleration, then it means that there you are again increasing the displacement. If you are deriving the displacement from the acceleration, you are again increasing it with t to the square. And it is that dotted line that you see there, this one. So if you go for a minimum acceleration, the displacement spectrum will go to infinite very soon. Now the question is, should we do this or should we do something better? Well, if you follow this approach, the general equation is here. So this is very trivial. It's just the displacement that we obtain as a function of acceleration. And if we do that, we could then try to correct the displacement spectra with some displacement reduction factor, which is similar to a force reduction factor, which is a function of ductility. There are equations of this sort, for example, in some different version of the Eurocode. This is just the square root of 7 divided by 2 plus the level of damping. But it could be, in other documents, there are level with a 10 here and the 5 here. The important thing is that the difference between these two is 5. So that if you put a 5 here, you obtain 1, and there is no correction, no displacement correction here. If you are, of course, assuming that 5% damping is your reference spectrum. And you could, and I will come back onto this, you could consider that you have a smaller effect of the damping on the reduction of displacement if you have records where essentially you have a single important pulse. This was somehow what was happening in the Whittier record. You remember the shape of the accelerogram was characterized by essentially one pulse, and therefore the effect of viscous damping was less. The reason is clear. The viscous damping, to act positively, need to have a number of cycles, needs time. If you had only one cycle, you have no effect. If you are pushing the structure, you cannot build on the capacity of the structure to react cyclically. So this is something that we could do. It's relatively simple. But we could do something better. And we could do something better, particularly in the long period range. Of course, this is a matter which is more typical of seismologists. But unfortunately, often seismologists are very good scientists, but they look at their own interest and not at the need of engineers. So there is a need of convincing some of them to look at problems that are of interest to us. And we have done some work together with some good seismologists, with Julian Bommer, with Ezio Faccioli, with other people. And what it is recognized is that it is true that a displacement spectrum could be approximated by a bilinear approximation. The bilinear approximation could imply a constant second branch or something that could even decrease in low seismicity areas. Or it will decrease at large period value. We should also look at other problems, for example, to the problem of soil amplification. And as I will discuss in a minute, we will see that actually soil amplification could have a larger effect on displacement spectra, on displacement demand, than on acceleration demand. And the third point is that soil amplification could have different effects at different distance from the source. So the equation that has been developed looking at the results obtained by seismologists are simple equations. Essentially, of course, we only need 2 points. We need to define essentially where the corner period is and the corresponding displacement value is. So what you see there is the first equation where the level of the corner period is approximated as a function of the magnitude only. This is still a kind of an open problem. There are codes that are assuming a constant value for the corner period that does not depend on the magnitude of the earthquake. There are other codes that are essentially correcting the level of the value of the corner period in a more than in a linear way, I mean in a kind of a quadratic or exponential way. And therefore, this is an approximation that which we will consider that is soundly based, but of course some new data could improve this relation. The other equations that you see down there is the formula that gives the value of the displacement demand at the corner period. And as you can see there are two parameters. One is the magnitude of the earthquake, which is in the exponent there. And the other factor is the distance, which is there at the denominator of the fraction. What happens if something of this sort? What you can see there is that there is a very, very important effect of both magnitude and distance on the, well, what you see here is the effect of magnitude, of course. But if I go here and I take the same magnitude at 20 kilometers distance instead of at 10 kilometers distance, you see that the effect is extremely significant. What you see here is that the difference between a magnitude 6 and a magnitude 7 earthquake is very large, both in terms of corner period and displacement demand. While you may remember that when we were looking at the acceleration spectrum for Whittier and for Northridge, you were at the same distance. One was a magnitude 6, the other was a magnitude 7 or something, and the difference in the acceleration demand was only around 2. And if you look at the distance, again the effect is dramatic in the sense that the displacement demand decreases very significantly as long as the distance increases, so that when you go to say 40 kilometers, you can have a significant displacement demand only for a very strong earthquake, for a very large magnitude earthquake. A small magnitude earthquake would have a significant effect in a very short distance from the epicenter or from the fault, as you wish. I'm sure that Nigel will discuss something on this tonight, presenting the effects of the Christchurch earthquake, which has been a very interesting earthquake under this respect. So if you take this as data to design, you may consider this as a possibility to define different level earthquakes for different performance level, or for different limit states, as you want to call them. Suppose that you want to define a serviceability limit state, and for some reason you decide that you have a 50% probability in 50 here for a magnitude 6. So this is a very high seismicity region, if you have something like this. But anyway, you can have something of this sort, and you end up defining your peak ground acceleration level and your peak spectral acceleration level, but also to define your corner displacement. Look at the tree value of the corner displacement there. You have 90 millimeters, 600 millimeters, 2 meters. But if you look at the peak ground acceleration, or even at the peak spectral acceleration level, you have a factor of, say, 2 and another factor of, say, 2. So what I'm trying to say is that increasing the level of earthquake, you are increasing much more significantly the displacement demand than the acceleration demand. But to do this is rather simple. Let's go back once more to these two equations. These two equations are very straightforward. If you accept them, there is no problem in defining your design earthquake, provided that you have some indication on the possible source mechanism and the distance of your source mechanism. I will say something more on preparing an ASM map just before closing this lecture in 5 minutes. So what happens is that if you use this data, the data that I was discussing now, and you use them into two possible frameworks of force-based and displacement-based design, what happens in a force-based design is that you enter an acceleration spectra with 3 spectra there, and normally, since you are assuming that you know the initial period of vibration, you are simply moving along a line here and just finding out your 3 level of spectral acceleration to design. And of course, there is a linear relations between these levels. There's no question. You are moving up along the same line. But what happens here is much more, I would say complex, but not complex in the sense that it's difficult, in the sense that you are not sure what will happen, because you will enter with 3 different levels of displacements if you want to use all these limit states, and for each one of them, you are going to hit a different spectral shape. And of course, this figure is drawn in this way to make it simpler, because actually we should say that this life safety has been corrected taking into consideration the level of ductility there, and this one has been corrected to a lower extent because the ductility demand is lower, and this has been correct. Maybe this has not even been corrected because you have been assuming 5% damping. But as you can see here, you are entering a different level, and you may even end up having something which is not so different in terms of displacement, or that it is very different. So what I'm trying to say is that you are not sure which one will be the situation that will govern your design. And this gives more flexibility and it will make the approach more interesting in a way. So let's start now again. Let's go back to this equation that gives you the displacement, and this displacement was given, say, in analogy to what happens with a force-based approach, in terms of, say, a firm ground. What is a spectral shape on a stiff soil? But you have then to do some correction on the displacement demand as a function of the characteristic of soil. And this is again something that you could do in a very simple way, in a much simpler way than in the case of the acceleration spectra, because what you can do there is simply to take some multiplier, and we believe that these multipliers are reasonable, but if some geologists or some seismologists will give us different figure, that will not create any problem in the procedure. Note anyhow that the multiplication factor are very large with respect to what we used to consider when we are dealing with acceleration. And they are much more close to what happens in reality. You can see that for soft soil, for very soft soil, you could have an 80% increase with respect to some level of firm soil, while in many cases the increase is maybe 35% or something in that range. This is just an indication to compare what happens. This black line here is the line that gives you the corner period as a function of the moment magnitude. What happens if you use the Eurocode 8, which we believe is very bad in this respect, is that you stay on the green line here. If you use the NER provisions, you stay on this red line here. And we tend to believe that both of them are exaggerating in one direction or in the other. This green line will be corrected very soon. I hope and I believe. This line here has been derived from some data that were obtained at the beginning of the last decades, and other data were slightly above this level. But again, to move from here to here will not change significantly the results. Now the correction factor. The correction factor, as we have been discussing, will be the factor that will reduce the displacement demand as a function of the equivalent damping. And I already pointed out that there are several formulations of the sort of something on a square root, under a square root, with a say, square root of 10 divided by 5 plus the equivalent damping, and so on. It is interesting to note that these are not new formulations. In '87, Newmark and Dole proposed a correction which was based on the logarithm of the equivalent damping. From our experience, this formulation here is giving better results than this formulation here, but there are studies going on this correction factor that may slightly change or make even simpler the correction to the displacement demand. And the other point is that to take into consideration the fact that when you're dealing with a strong pulse with some sort of forward directivity in near field, the effect of viscous damping is less. In our book, there is a proposal to change the exponent of this parenthesis and reducing it to 0.5 to 0.25. This has been just a brilliant guess of Nigel, so there is not so much seismological studies, but we believe that this is appropriate. And you can see here a comparison of the correction factor between the expression that I was showing, the one produced by Newmark and Hall in 1987, the two other expressions. And this is the kind of correction that you obtained. As I was saying, if you make a mistake between, say, 0.15 and 0.20, this is not so crucial, much less crucial than assuming a completely wrong force reduction factor. And this is a scheme of the kind of correction that you will obtain with a 0.5 exponent or with a 0.25 exponent. You see, this curve is the same as this one. With the 0.5 exponent, you are reducing the spectral shape much more than with the 0.25 exponent. One last, okay, this is everything is written, so you just read this enough. But one last point that I would like to point out is that going back to the basics of design that I was discussing earlier, you remember that I was saying you enter with the design displacement, hitting the appropriate curve, which is based on the estimated damping, and reading a period of vibration. Of course, you can put everything together and immediately calculate a base shear as a function of the equivalent damping, of the appropriate exponent, and so on. But what we have to discuss briefly is what will happen in a case like this when your design displacement or elastic displacement demand is above your spectral shape. In this case, the answer is very simple. You could design for any period of vibration which is exceeding this value, and therefore, in a way, you don't have a unique choice for what concerns your strength. I think that tomorrow there will be more examples on this aspect. But if you, on the opposite, have something like this, where you are designing, of course you can correct your, you cannot correct this because this is the delta y, but you can correct the design displacement. If you have something like this is the target displacement for a certain level of ductility. So the difference between this level and this level is that this is a yield displacement and this is a design displacement. So what happens here is that you are below the curve represented by the 5% damping, but you are above the curve which corresponds to your design level. What should happen here is that you are making two assumptions that are not consistent between them. You are assuming to go to a certain displacement, and you are assuming to have a certain level of dissipation of energy. So what you should do, sorry, it's here. What you should do, the other one, I'll go back to that. What you should do is to correct your design displacement, reducing it, which will increase the level of this displacement because your equivalent damping will decrease and therefore the other spectral shape will go up. And you may iterate maybe 2 times, but not more, to go to something where you can have now this level corresponding to this level and design for your corner value. And this was what I was trying to say. If the elastic period will exceed the corner period, you can design for anything you wish, and the design-based shear force will be essentially the elastic stiffness this stiffness here multiplied by this level of displacement. Now, one last consideration, and so I close on my country, is that you obtain very different results if you look at seismic hazard maps in terms of acceleration or in terms of energy, or in terms of displacement. And actually what happens is that a displacement map is normally much more dramatic, is more emphasized. The difference between, strong earthquake areas or lower earthquake areas are more emphasized. You see, this is an acceleration map for a certain value of return period. I believe this is for a 500, but doesn't matter. I think it's for a 10% in 50 years, but doesn't matter. You can see that you can go to level where you have 0.3 G on firm ground and so on, and so on and so on, and having a large number of levels of acceleration demand. We have a map where we can read online, open to anybody. We can read online all the acceleration demand, spectral shapes, and so on at 2 kilometers distance in all in all the country. But if you look to produce something similar to that in terms of displacement, first of all, you have to decide what kind of displacement you want to represent there, and those values are displacements for a period of vibration of 10 seconds. So, assuming that this is a reasonable evaluation to give us something which is, say, representative of the seismic action. But as you can see, there are areas, you see the gray areas there, where the displacement demand is less than 1.5 centimeters. So while I have been fighting for years to have the whole area of our country to be considered seismic prone and to be mandatory to design for earthquakes, it is clear, if you look in terms of displacement, that you may end up to have some area where the displacement demand is so small that you do not really need to design in a proper way for earthquake. You only need to follow some basic rules of good detailing and nothing more. Because a structure, I think you agree with me that essentially any structure should be able to reach a displacement of 1 or 2 centimeters. And of course, you will end up also with very different spectral shapes, and I won't enter in detail into this matter, but I think that it will be interesting for those of you who are dealing with the seismic code for Costa Rica, maybe to go in some more detail into this aspect. Finally, to close, I am only 2 or 3 minutes late. In the notes that you have, there are 3 final slides on lecture 2 where there is a design, an homework assignment. So we all hope that tonight you will design this structure, which is very simple. You will not need a lot of time to do that. But just to see, and maybe to ask questions tomorrow to see whether this approach works or not. So you have here a very simple structure, which is a bridge column. And we propose that you try to design this using force-based and displacement-based design with a ductility equal to 3 and with a diameter of 1.5, 2, and 2.5 meters, and with an acceleration, a peak ground acceleration of 0.4 g. So we provided there the value of the mass, which is 6,000 kilonewton divided by g. And maybe if you should be willing to do so, you may also change the peak ground acceleration to 0.2 and 0.8, which is half and 2 times. And if you do that, you will have some indication on how the results change in a different way, applying a force-based approach and a displacement-based approach. And there is an indication of what you could use as the elastic modulus and the yield strength of the steel, and an approximation that you could use to guess what the correct value of the inertia is with respect to the gross value of inertia.
That's just for the force-based design.
Of course. In the case of displacement-based design, you do not need to do that. In force-based design, if you want to use the gross stiffness, you could do that, but you will end up with even more wrong results. And anyway, this is written in the next slide, and in the final slide there is some indication of the basic equations to be used that anyway have been discussed in this and in the previous presentation. This is just a summary so that you can do that if you wish in a very short time. And I think we can finish here.